Hi again everyone, it's Chris Tisdell here, and in this presentation I'm going to show you how to solve the following problem from partial differential equations. Now the method that I'm going to show you is called the method of separation of variables. So this is a very powerful method that can be used to solve all sorts of different PDEs. Now you can see here we've got a second order PDE. This is known as Laplace's equation in two dimensions. By the subscripts, u sub xx, u sub yy, I mean the second partial derivatives of u with respect to x and with respect to y. Now, we've also got some extra conditions here and here, and here. These are sort of side conditions, if you like. And we've also got a limiting condition on u. So what we're going to try to do is solve the problem for the function u, which depends on x and y. Now sometimes with these problems what I like to do is start with a little diagram. Okay, so here we're trying to find the solution u for all x positive and for all y between 0 and h. Okay, so what do these extra conditions mean here? Well, if we think of u as, say, the temperature at any point xy in this shaded region, essentially what we've got here is like a semi-infinite bar. Okay, so if you use the steady state temperature at any point x comma y inside that bar, then these conditions mean that along this edge of the bar, the temperature's always 0. This one means along this edge of the bar, the temperature's always 0. Down here, this edge, the temperature is identically equal to 1. And here we have a limiting condition. It means that as we move to the right for any y, the temperature must go to 0. So how do we solve this problem? Well, it relies on this method known as the method of separation of variables. The method is quite long. So if you're watching this video, make sure you get comfortable because the process is quite lengthy. Now, when you solve these kinds of problems, you wouldn't necessarily write down and take as much time as I'm going to take because I'm explaining everything as I solve the problem. Okay? So, the fundamental assumption with separation of variables is to assume that a solution to the PDE involved is of a special form. It's the product of a function of one variable with a function of the other variable. Okay, now based on that assumption, what you do is you look at your original PDE and calculate the derivatives or the partial derivatives that appear in your PDE. So I can see u sub xx and u sub yy appear in my PDE and nothing else. So from this form, let's calculate u sub xx. Well, we take this and we imagine y is a constant and we differentiate everything normally with respect to x. So essentially this, because we're multiplying two things together, this basically plays the role of a constant. Okay, so u sub xx here is just f double dash of x times g of y, where by the double dash I mean the regular derivative with respect to x in this case. Now if we calculate u sub yy, well it's just very similar. F of x will just be a constant and you differentiate g with respect to y. Okay, so the g double prime or the g double dash means the regular second order derivative of g with respect to the variable y in this case. Now based on that information we can then go back to our PDE and form two ODEs. So now we take our PDE from the top, sub this and this into the equation and form a new sort of ODE setting. Okay, so let's see if we can accommodate that. So if we sub into our original PDE, we're going to get the following. Now, as the name separation of variables suggests, what we try to do is separate the variables, the independent variables, right? The x's and the y's. Okay? Once we have that, we know that basically the ratios involved must be constant, equal to some separation constant. Once we introduce that, we get two ODEs. Okay, so if I rearrange this, separate the variables, get all the x's on one side and all the y's on the other via division or multiplication, we'll have the following. Okay, so basically if I take this to the other side and divide by big F of x and big G of y, I'll get the following. Okay, so now I can argue that these two ratios must be equal to a constant. Why? Because on the left-hand side, I've got functions involving x. So if I vary x, I'd expect the left-hand side to vary. But the right-hand side doesn't have any x's, so it can't vary, but the two things are equal. On the right-hand side, I've got y's. So if I vary y, I would expect the right-hand side to vary. But that's equal to the left-hand side, and the left-hand side doesn't have any y's in it. So it can't vary. So the only way of explaining this is the following. These two things must be equal to a constant. So this is called a separation constant. Now I'm just going to call it, say, sigma. Okay, now I've dropped the arguments off the big F, big G, etc., just to save a bit of space now. Okay, so now from this I can form two ODEs. Okay, so if I take the F up there and rearrange, I'll get big F double prime minus sigma F equals 0, and the same with the G double prime. Okay, so remember, big F is a function of x, big G is a function of y. So now we have two ODEs, okay? So we've set up two ODEs. What we're going to try to do is solve them by involving the boundary conditions in some appropriate way, or the extra conditions here. Okay, so I'm going to call this A and this equation B. Okay, so let's have a look at our extra conditions here. I'm going to employ these two conditions first. Okay, so we've assumed that a solution to the PDE is a product of two functions, big F of x times big G of y. If I concentrate now on these two conditions, we get that from the first condition. So what does this tell us? It tells us that big F is identically equal to 0, or big G of 0 is 0. Now we don't want big F to be identically equal to 0 because that way we get the trivial solution. Okay, so we get some condition involving big G of 0. What about the other one? Well, that's just okay, so in this context, again, big F is identically equal to 0 or big G of H is 0. Now, if big F is 0, the product F times G is 0, so that's not, that's trivial. So we will conclude that this is our condition. So what we're going to do is solve this subject to the two simplified boundary conditions involving big G. Okay? So if we look at the differential equation B, how do we solve that kind of problem? It's a second order homogeneous ODE with constant coefficients. You set up your characteristic equation and you look at the roots. Are the roots real and unequal, or are they complex? Okay, so that's the next sort of phase. So let's call a characteristic equation now, depending on whether sigma is positive, negative, or 0, we're going to get different roots for that bottom line. Okay, so the simplest case is probably when sigma is 0. When sigma is 0, well, we get lambda 0, so real and equal roots. But if you just sort of look up here, you'll have just G double prime equals 0. So you integrate that twice to get something like AY plus B, where A and B are constants. Okay, so that's the simplest case. Okay. So when the separation constant is 0, this has real and equal roots, or alternatively, this term disappears. So integration 2 times will give you the following. Okay, so what we want to do now is determine big A and big B. We do that from the boxed boundary conditions on the right here. So, let's take the first one. Plug in y equals 0, I'll get B. And if I plug in, so B equals 0, if I plug in H with B already equal to 0, I'll get AH. Now H is positive here, so A must be 0. All right, so we end up with a trivial solution. Now we're not interested in the trivial solution. We're looking for non-trivial, non-zero solutions to our problem. Okay? All right, so what now? Let's discuss the case where this separation constant, sigma, is negative. Okay, so in that case, when sigma is negative, the roots of the characteristic equation are going to be real and unequal. Okay? So when the roots of the characteristic equation are real and unequal, the general solution is a linear combination of exponentials. Okay, again, A and B are just constants here. Okay, so this is the roots of the characteristic equation are real and unequal. Now remember, the sigma is negative in this case, so root negative sigma makes sense, if you like. Okay, so let's combine this form with our two boxed boundary conditions and see what happens. Now, those of you who have done these kind of questions before, you probably notice a pattern now. We're both going to get A and B equal to 0. But let's just go through and verify that. So big G of 0 is equal to 0 from up here. So I go here and plug in y equals 0. So I get A plus B. So that doesn't tell me too much, but let's go through and use the second boundary condition at H. Okay, so I go in here and plug in y equals H. Now, from the first equation, I can simplify the second equation. A equals negative B. So I can actually take a common factor out, say of A, and I get something like this. Okay, that's a negative sigma there. Okay, so if that bottom line is equal to 0, well, either A is 0 or the thing in the square brackets is 0. Now, trust me, the thing in the square brackets cannot be 0. The only way it can be 0 is if the sigma is 0, because then you get 1 minus 1. Okay? But hang on, sigma can't be 0 because we're discussing the case when sigma is negative. Okay? So we note okay, but we're not interested in that. Well, we're not actually discussing the case when sigma is 0 here. Okay, so the square bracket cannot be 0 in this case. So what do we get? We get if A and B in our g of y is 0, we get the trivial solution again. So we can ignore the case when the separation constant's negative. Now we get to the interesting part where, okay, let's talk about the positive values of the separation constant. Okay, so we return to our characteristic equation. We sort of go, okay, well, when sigma is positive, what's going to happen? I'm going to get lambda squared equals negative sigma. That's going to have complex roots, right? That's going to have complex roots. So complex roots with 0 real parts, so purely imaginary roots. So in this case, the general solution is a linear combination of cosine and sine. Okay. All right, so again, the A and B are constants, which we'll try to determine from these boundary conditions. Okay, so this is where it starts to get a little bit more interesting, a little bit more non-trivial, no pun intended. Okay, so if we put in the left boundary condition, what's going to happen? Well, that'll disappear and we'll get A there because we're taking A cos of 0. All right, well, what about the second condition? This is where the action happens. So this term's going to be 0, so let's plug in h into this for y. So I get the following equation. Now, you look at that and you go, okay, well, that equation is satisfied when the constant b is 0. But we're not interested in that because if a is 0 and b is 0, we get the 0 solution, the trivial solution. Or when the sine function is 0. Okay? So the sine function is 0. It oscillates up above and, it oscillates up and down 0 or across 0 many times. Okay, so let's discuss that. Okay. So, when does the sine function cut the axis, right? When is it 0, the horizontal axis? Well, it's 0 at multiples of pi. Okay? Now, we're discussing the case when sigma is positive, so we're only interested in positive values or positive places where the sine function cuts the x-axis. Okay, so this is why I'm just considering the sort of the positive multiples of pi, where n's an integer. Okay, so we went looking for b, but we've come up with something else. Now, if I rearrange this and say make root sigma the subject, I know this term's 0, but I can actually form a sequence of solutions here that are non-trivial. So if I just sort of rearrange that, so I get the following. And if I say square both sides, I'll get the following. Okay? Okay, so what do we do with it? Now, essentially, notice we have basically a sequence here. This is a special sequence called a sequence of eigenvalues. Now, eigenvalues is used in a different term here, or a different way than the eigenvalues you know from matrices, but there are connections. Okay? There's an infinite number of them, and they go off to positive infinity as n gets large and positive. Okay? So you can even, if you really wanted to, you've actually got a sequence of values there. So that's what the subscript is illustrating. Okay, so let's replace root sigma with this in our function. Now, because we have, or sigma sub n if you like, because we have a sequence of values there, we actually have a sequence of g's. So the little subscript n is going to denote each function or each solution to the problem that we've been considering. Okay, so I'm going to go up here, replace root sigma with n pi on h. Okay. Now, what is the b sub n here? The b sub n are just arbitrary constants. Okay? Now, you may go, why do I need a b sub n there? Well, 1b is not going to cut it because you need to sort of have a different arbitrary constant for each value of n. Okay? That's why we put in the b sub n instead of just a b. Just b alone doesn't cover it. Okay. Now, we spent a lot of time solving this problem subject to these boundary conditions. we still haven't solved this problem. So this is the next phase of the solution method. Okay, this again is a second order linear homogeneous ODE with constant coefficients. Now, we're only interested in the case that we just discussed, the case where the separation constant sigma is positive. So we don't have to go through and discuss the three cases again. Okay, we just have to worry about solving this problem for sigma positive. Okay. In fact, you could actually solve that problem, solve problem A, by just replacing this sigma with this. And you get a whole sequence of problems there. I'm not exactly going to do it that way, but it's equivalent. So, for problem A, the characteristic equation okay, and for the non-trivial case that we discussed, when sigma is positive, what kind of solutions are we going to get to our characteristic equation? We're going to get real and unequal roots, right? Because sigma is positive here. So I'm going to get exponentials, a linear combination of exponentials to the general problem A. So they're real and unequal roots. So the solution to A will be yeah, I can do that, yep. Okay. So now what we want to do is find those constants, big V and big W. So we need to use some sort of information here to determine them or discuss the ideas further. Okay. Before we get to that, let's actually replace root sigma with this, because that's the case, they're the cases that we're interested in. So we can actually form a sequence based on our prior working, just by basically replacing root sigma with this and putting the coefficients as a sequence. Okay. So this is for n equals 1, 2, 3, etc. Okay. So what haven't we got yet? Well, we haven't got these coefficients yet, and we're going to get those from the extra conditions that we were given at the start. Okay. So we've used this. We've used these, we haven't used these yet. Okay, we haven't used that information yet. Okay? Now, going back to our original assumption that U is just a product, or a solution is just a product of the two functions of x and function of y, what we can do is multiply these two sequences together, and then I've got, basically a sequence of solutions. So for each value of n, the product is going to be a solution to the problems that we've encountered so far. Okay? Okay, this is for n equals 1, 2, etc. Okay, so how are we going to determine these constants, or the sequences, I guess, or sequence of constants? Well, we haven't used this limiting condition yet. What it says is for each y between 0 and h, if we let x tend to infinity, the temperature, if you like, approaches 0. Okay, so let's look at this product for a second. If I let y be any value between 0 and h, some bounded value, how can this product go to 0 as x goes to positive infinity? Well, as x goes to positive infinity, this is going to go to 0, right? Because the exponential to a negative is going to go to 0 as x approaches positive infinity, right? But this term, the only way this term can go to 0 is if all these coefficients are 0. Okay, so essentially to agree with this limiting condition, we can simplify by, I guess it's necessary that all these constants have to go to 0. So that term will disappear. Okay? If and only if this term, okay, is 0. So that eliminates that part. So essentially what we're left with is a product of exponential with a sine function. Okay, now you've got these two constants here which you can multiply together and just label a new sequence of constants just to make the algebra a little simpler. So I'm just going to make it b sub n, little b sub n. Okay? Okay, so we have a sequence of solutions to the problems that we've looked at so far. The last couple of steps involve the superposition principle and Fourier series. So what's the superposition principle? It says that if I have any two solutions to the problem and I add those solutions together, then the sum is also a solution to the problem. Okay? So, by superposition, we take our sequence and we sum them all up over the n's in this case. Okay? Now, if we can determine the coefficients, the b sub n's, then we've finished the problem. Okay? But we haven't used all our information. Okay? So essentially I'm summing up these sequences. We haven't used all the information yet. What haven't we used yet? We haven't used the final condition. This one here, the temperature is a function, in this case it's just a constant along this edge or this boundary. Okay? So, this is where you may or may not involve Fourier series. So using the final condition, let's take our crazy looking sum and plug in x equals 0. I'm going to get e to the 0, which is just 1. And I'm left with a series involving a sine function. So, what is this? It is a Fourier sine series for the constant function 1. Now, from Fourier series, how do we calculate the b sub n's for a Fourier sine function? Well, it's just used as an integral formulae. Okay? Let's go with, yeah, I could use f here, yep. Okay? So the Fourier sine series for a function has its coefficients given by an integral formula. It's 2 times the following. Okay, so in lectures, the H is playing the same role as L in your formula sheet, okay? So if you know the Fourier series, you'll know that, okay, we look at periodic functions that are piecewise continuous, etc. And a periodic with period 2L, okay? So the H is playing the role of L in this context, okay? So, from between 0 and h, our f is just identically equal to 1. We don't know what h is, so we're just going to leave it. So we're integrating something that's not too difficult. We don't have to integrate by parts, which is good. So let's carry out this integration, integrating with respect to y. Okay, so integrating with respect to y, we note that sine goes to negative cosine. I'll get something like this. And so you can see that the h's are going to cancel off. And I can take these out the front, and then I just need to plug in the values for y. So the first we'll get cos n pi h all over h, so the h's will cancel. So I'll get cos n pi. And the second is just cosine of 0, which is 1. So now we're going to simplify this a bit more. We know that cosine n pi, where n equals 1, 2, 3, 4, etc., is an oscillating sequence. It oscillates between positive 1 and negative 1. Okay, so one way of writing this is in the following form: minus 1 all to the n. Okay, so now if we look in this square bracket, the first term is going to be positive when n's even, and this term will be negative when n's odd. So I can simplify even more. If n's even, I'll get 1 minus 1 here, so the square bracket will be 0. And if n's odd, this will be minus 1, and in the square bracket will be minus 1 minus 1, which is negative 2. So the whole thing will be 4 on n pi, for n odd. Okay. So now what we can do is we've calculated the b sub n's. The b sub n's are 0 when the subscript n is even. And if n's odd, it's 4 on n pi. Okay, so what I can do now is write this out in the following way. Okay, so as we noted from our boxed expression back here, this is my Fourier series. Now, for every even value of n, this coefficient is 0. So I'm adding up lots and lots and lots of zeros in this. Okay, so what I'm going to do is actually just sum over the non-zero terms. Okay, so the Bn is 0 for n even, but it's not 0 for n odd. So I'm only interested in the odd values of n, which lead to non-zero values of this coefficient b sub n. Okay, now you might think, okay, well, this looks a bit odd, this summation sign. Here I'm subbing, over n equals 1, 3, 5, 7, etc. And this, you can possibly leave it in that form, but I want to go one further where we sum over, 1, 2, 3, 4, etc. So what you can do is replace n in here with some odd value. I'm going to replace n with 2k minus 1, where k is 1, 2, 3, 4, 5, 6. Okay? If k is a natural number, then 2k minus 1 is always odd. So I can take this 4 on pi out the front. That's got nothing to do with n. And I'm going to sum from k equals 1 to infinity and replace n in the summand with 2k minus 1. So there you have it. There's your final form of your solution U. Now, some people may write this instead of 2k minus 1, down here you have 2k plus 1 and start the k's at 0. That would be fine as well. So let me just recap what we've done. We've assumed a solution's in this form. We calculated the derivatives that appear in the PDE. From that, we formed two ODEs via a separation constant. Then we discussed one of the two PDEs and introduced some boundary conditions that were derived from these side conditions here. Now we discussed various cases for that separation constant. Okay, in two of the three cases for this particular problem, the only solution to the problem was the trivial solution, which we ignore. When the separation constant was positive, we ended up with a sequence of solutions. Okay. Okay, we formed this sequence of solutions. And in turn, there was a sequence of solutions to the other ODE that we formed. Okay, now we then went through and tried to calculate these coefficients. So how do we do that? Well, we used some of the extra information given to us at the start of the problem. You can see in this case we've used the limiting condition. Finally, we formed a sequence of solutions to the problem and then use superposition. We added up all those sequences of solutions to form this general series involving this exponential and a sine. Lastly, we used the final condition, which was this condition here. Okay, so we realized that condition leading to this is just a Fourier sine series for the constant function 1. Okay, so we know from the theory of Fourier series how to calculate these coefficients. It relies on integration. We carried out the integration and then wrote out the solution in its final form. Now that's a long problem, but hopefully you can see there are 3 or 4 steps. Each of those steps is quite lengthy, but you can do it. You need to be confident with these problems and also manage your time appropriately. Now I've tried to explain this problem in detail as I go along. You wouldn't necessarily spend as much time as I have if you're, for example, doing an exam question involving something like this.